Department of PCE, SJBIT. In this session, we will be learning about Module 1 second part, which is a transmission line followed by the analysis. A transmission line usually, which is nothing but it is the component which is responsible for the transmission of signals are called as a transmission lines, and they can take various shapes and can be in any form. And some of in general we know that in circuits or networks which are made up of some of the components which will perform the operations on the signals, and some other components, if you see, they'll carry signals from one place to another place with minimum amount of distortion on the signals. So transmission lines are the one which are responsible for the transmission of signals. Okay, so transmission lines are the one which are responsible for transmission of signals from one place to another place in a microwave circuit, and they can take they can be in various. You observe this is a coaxial cable, which is a one form of transmitting one form of a transmission line with two conductors, center conductor and outer conductor, separated by a dielectric. Another form of transmission line is a two-wire parallel transmission line. So two conducting wires which are running in parallel and separated by an air are dielectric, and the electric and magnetic field formation which you can observe in the graph. And another form of transmission line is a strip line. So here you can observe the two layers, top layer and bottom layer, which are of conductor, and in between middle layer which you have, that middle part is separated from the ground plane by a dielectric material which is of epsilon r. And another type of transmission line is a microstrip line and the waveguide type. In microstrip line, same as your strip line, but major difference is you have a ground plane which is a conducting one, and upon that you have a top layer where your strip line, microstrip line, will pass the which is a conducting type, and these two layers are separated by a dielectric. In the same manner, if you observe, they are, as I have informed, it is mainly used to transmit energy from one point to another point. So sometimes we can also make use the transmission line as an inductor or as a capacitor or a resonant circuit, filters, and also be used as a measuring device at high frequencies. There are basically four types of microstrip lines. There are four types of transmission lines: two-wire parallel transmission line, coaxial line, strip line, and waveguides. We will see each and every one in detail. Waveguides, if you see, waveguides are nothing but the hollow structures. They have a hollow structure, single metal pipe, and can propagate the signal having a frequency, high frequency. That means they'll give the lambda c, that is a cutoff frequency. They'll allow the signal greater than cutoff frequency, and it can allow TM or TEM wave propagation. TM and TEM are TE propagation, indicating transverse magnetic, transverse electric, and transverse electromagnetic. And they can handle larger amounts of power compared to other strip line, other lines, other transmission lines. They are immune to more. They are immune to interference and have a less signal distortion. Lossless means even in some cases you'll get a lossless case. Okay, and this is one but the problem with this is waveguides, as they are bulkier, cannot be made use in MICs. MIC indicating a microwave integrated circuits. In the integrated circuits, it is not possible to use waveguides. Now we will look into the transmission line theory. In transmission line theory, we'll be dealing with the two-wire parallel transmission line. So the two-wire parallel transmission line analysis. As we know, normal capacitor, inductor, and resistors, if you observe, lumped components. Those lumped components which will be at low frequencies, if you observe, as the frequency of the signal, which is from frequency, if you calculate the wavelength, As frequency is low, lambda value will be very high. The wavelength is not incomparable to the component size. Whereas in the distributed case, suppose if I operate at very high frequency, the elements will become from lumped to distributed. Why it will come into picture means the wavelength is incomparable to the size of the component. As it is at very high frequency, lambda value, which is C by F is very large. Obviously lambda value will be very less. So lambda, that is wavelength, which is in comparison with respect to the size of the component. So you can't make use of lumped components in high frequencies, at high frequencies, and different losses that you will have, dielectric loss, different types of losses that will occur. So to analyze a transmission line, we will be using a distributed circuit elements. So usually they'll account for the propagation and the time delays, that is a phase change. So in the transmission line, to analyze the transmission line, we will be using distributed circuit parameters instead of lumped parameters. All these distributed circuit parameters, they will be distributed along the length of the line. The reason for that, as just now I said, the length of the line is significant compared to the wavelength. Then in the same way, as I have specified, you can consider it may be either a two coaxial cable or a two-wire parallel transmission line. For the analysis, to make it easy to have an analysis in calculations part, we will be dealing with two-wire parallel transmission line. So in that two-wire parallel transmission line, all the components are distributed along the length. So if you observe the length of the this is the length of the transmission line, yellow color one. So delta Z indicating a small section of transmission line we will be considering, not the whole length, a small section of transmission line is considered. And in that section of transmission line, if you give or if you feed the signal, all the components, means all the elements, circuit elements are distributed along that along that length. So the distributed components exists in this section of transmission line can be seen as capacitance per unit length and inductance per unit length. All the values are measured per unit length per meter. Inductance units are henries per meter, resistance ohms per meter, and conductance mhos or siemens per meter. All the components are distributed along that transmission line, which one for the section of transmission line if you consider. So now we need to analyze this transmission line. Analysis indicating I need to find out, I must be in a position to find out the voltage or the current variations, or it may be a power variation at the other end of the line by giving the input from one end. So can we be able to model this transmission line, or can we be able to find out, do the analysis same as your lumped components? Yes, we can do by equating, by writing an equivalent circuit. So you will be writing an equivalent circuit and analyzing that equivalent circuit by using normal circuit theory, and you will be determining at the other end the voltage or current values. So for that you can observe you have four components, four distributed components, and which are measured per unit length, which will be represented in this manner: resistance and inductance in series and conductance and capacitance in parallel. And we are considering for a section of transmission line which is a delta Z. So input which we had given is voltage, and you can observe it is varied with respect to Z and T. So two parameters with respect to two variables you can find out. So usually time varying components will be specified, and as it is a distributed one and it varies with respect to the time space also. So that space component which we are representing here as Z, meaning we are placing the transmission line along Z axis. Okay, so if I consider x, y, z rectangular coordinate system, consider the transmission line which is placed along the Z axis, and in that a section of transmission line of length delta Z is considered. To analyze the output, I will be writing an equivalent circuit of that section considering the distributed parameters as RLGC, resistance, inductance, conductance and capacitance. And the voltage and current values which we are considering are varied with respect to two parameters. One is with respect to the time, another one is with respect to the space, that is Z. So at the input side, I am considering the voltage applied as V of Z comma T and current applied as I of Z comma T. As soon as the voltage and current passes through this equivalent circuit, at the other end, delta Z, once if it passes through delta Z, I must be in a position to find out the voltage and current. So before we go for that analysis, how we can write that section of transmission line as 4 elements. Why only these 4 elements? Suppose if I consider the conductor, as I have specified, it is a 2 conductors which are separated by 2 wire parallel transmission line. I am considering 2 conducting lines separated by a dielectric of epsilon r, or it may be unity, or air, it may be air. So when we consider 2 wires, 2 conductors separated by a dielectric, which will be considered as an equivalent circuit having a capacitor. We know the capacitor is nothing but 2 parallel plates, 2 conductors which are separated by a dielectric. So you can consider the 2 conducting wires in parallel running can be considered as a capacitance existence. The leakage in that dielectric will be represented as a conductor, that is conductance part, that is G into delta Z. Similarly, the resistance and the inductance part, if you consider, whenever the current, if you apply, whenever current flows on both the conductors, which is in opposite direction, obviously it induces a magnetic flux density between those 2 conductors. So that magnetic flux density, you can represent that as a inductance, L value. And leakage in that will be represented, that is a loss. Conductor with a finite conductivity you will be making use. Any loss in that, that is a heat loss, that can be represented as a equivalent resistance. Similarly, the capacitance and conductance, these two represents the losses. So you can represent the 2 wire parallel transmission line as you have 2 conductors separated by a dielectric, representing that as the capacitance, and the leakage, dielectric leakage, will be represented as a conductance, and due to the current flow you will have a magnetic flux linkage, that is represented as an inductor, leakage in that represented by the resistor. So RLGC is an equivalent circuit for a section of transmission line which we are considering. R is resistance per unit length, so that is ohms per meter. Delta Z, if I consider in meters, which will cancel, will have a resistance only. Similarly, the other parameters also. So now I wanted to analyze this. So to analyze this, we will be applying, it is same as your circuit theory. You have a network. You will be analyzing that by finding, I need to determine voltage and current at the other end. So for that, you will be applying a KVL and KCL. You have 4 components, 2 components in series and 2 components in parallel. So you can apply circuit theory, that is KVL or KCL, to determine, you can find out the voltage and current on a transmission line based on the circuit model. That is by applying KVL and KCL, Kirchhoff's voltage law and Kirchhoff's current law. One by one we apply and determine the voltage and current. So first one, by applying KVL. So according to KVL, as we know that according to Kirchhoff's voltage law, the voltage drop across the closed circuit must be equals to 0. Potential rise in potential and fall in potential in a closed path must be equals to 0. So we start from one point. Across this parallel component we will have a, we know the concept as current flowing through the series elements is same, voltage across the parallel elements is same. So across G and C, we will have a same voltage V of Z plus delta Z comma T. And now we apply KVL for this first loop. So current flowing through this is considered as I of Z comma T. So drop developed across the resistor and inductor. So drop developed across the resistor will be V is equal to I into R. So I of Z comma T into R into delta Z. Similarly, drop developed across the inductor will be voltage drop V, voltage across an inductor, V is equal to L di by dt. Now L is L into delta Z. So current variation, differential current variation, dou I of Z comma T by delta T. Now you apply KVL for this loop. Considering a current is flowing in this direction, develops a drop across this each element as minus plus, plus minus, plus minus, plus minus. So V of Z comma T, you need to consider minus plus, plus minus, opposite in direction. So minus I into R of R into Z of T minus L into dou I by dou T. Again it is plus minus V of Z plus delta Z comma T equals to 0. Rearrange the equation. By rearranging, you can write, I am interested in finding out voltage and current at the other end. So you can rewrite the equation representing voltage at the output is equal to whatever you have applied minus drop across the inductor and drop across the resistor. Similarly, you apply KCL. According to KCL, Kirchhoff's current law, we know that current entering must be equals to current leaving. So at a node, so here I am considering a node as one node junction of two or more elements. So at this node, current entering will be I of Z plus Z comma T. Current leaving is I of Z plus delta Z into T. So I need to determine I of Z plus delta Z comma T. So you can apply KCL. According to KCL, current entering I of Z comma delta Z comma T. Current leaving through conductor and capacitor. So current, if I want to determine, I is equal to C dV by dt. So C value is C into delta Z, dou V by dou T. Voltage drop across that. So similarly, current through this conductor is, which is G into V. So G value is G into Z multiplied with the voltage drop across that. So we have applied KVL and KCL, written a governing equation, rearranged that equation. So now again, to determine the voltage and current, we will be considering voltage and current as with respect to, varied with respect to the time first, because sinusoidal signal, let us consider we have applied. So if I apply sinusoidal current, the voltage and current can be represented in a real part as V of Z into e power j omega t, and current as I of Z into e power j omega t. Now you derive this, differentiate this equation with respect to time. So after differentiation, you substitute into this equation. So after differentiation, if you substitute the voltages and if you determine time function, already you have substituted, no? So that's why here I am not considering the time variation. Already here we have imposed. So now E of Z plus delta Z will be equals to V of Z minus L into delta Z. I am differentiating dou I by dou T. So I am differentiating this with respect to time. If I differentiate, you will get j omega into I of Z. Similarly, the other component R delta Z into I of T. Rearrange the equation. So by rearranging the equation, you will get the KVL and KCL equations. If you rearrange, representing that, taking voltages on one side and differentiating that with respect to delta Z and making that delta Z as very small, which is nothing but dV by dZ. The other side which you are left out with is j omega L into I of Z minus R into I of Z. Similarly, the current equation, you can rearrange the expression in the previous slide. By rearranging this, you will get the governing equation di by dz as C into j omega into V of Z minus G of Z. So you can represent the same thing as by taking I of Z common. If I take I of Z common, you will be left out with minus of R plus j omega L. You can also call that as series impedance Z. And in the same manner, in the current equation, take V of Z common on the right hand side. You will be left out with minus of G plus j omega C. So G plus j omega C, which we call it as a admittance, shunt admittance, so which is Y. So we have got the governing equation. We call these two equations as a governing equation to find out the solution of voltage and current at the other point in a transmission line. So now the two parameters which we have here seen is Z and Y. So Z we call it as a R plus j omega L series impedance, and Y we call it as a shunt admittance or parallel admittance. All these are measured again with per unit length only, G plus j omega C.